In this video, we will study in detail how to find the general solution of second-order linear equations with constant coefficients that are homogeneous. So first of all, what is the most general form that such an equation can have? Well, it can have a constant coefficient a times y double prime, because it's second order, plus b times y prime, plus c times y, equals 0, okay, because it has to be homogeneous. And here, a, b, and c are numbers, okay, so just real constants. Now, I'm going to first describe where the next step comes from. So in particular, we will consider always an associated quadratic equation. But why do we do that? I'm going to try to explain it now briefly. Basically, we make the following ansatz, which means guess. We guess that a solution of this equation will have the form of an exponential. So let's say we predict a solution to be of the form of an exponential, e to the lambda x, where lambda is a parameter to be determined. Now, what would be the value of lambda if this function must satisfy the equation? Well, let's impose the condition that this function satisfies the equation. So we know what it means to be a solution. It means that if we plug it in, we get an identity. So let's compute the derivatives. Y prime will be lambda times e to the lambda x. Remember, lambda is a number. And y double prime will be another lambda, so lambda squared, e to the lambda x. Now, if I want this to be a solution, I will plug it in, therefore obtaining a y double prime, so a lambda squared e to the lambda x, plus b y prime, so b lambda e to the lambda x, plus cy, so plus c e to the lambda x. All of this must be equal to 0. Now, can I find values of lambda for which this is true? I can, because first of all, I can notice that since e to the lambda x is never 0, I can divide all terms of the equation by this, and therefore simplifying it. And I obtain a lambda squared plus b lambda plus c equals 0. And this is an algebraic equation whose unknown is lambda. It's called the associated quadratic equation. So in particular, this means that if lambda solves this algebraic quadratic equation, then the function e to the lambda x is going to be a solution of the differential equation. So now, this is basically to motivate why we will use this equation. We don't need to do this process all the time. We're just going to remember this quadratic equation. And let's just observe how you can obtain the quadratic equation simply by looking at the original equation. So you see, you basically keep the coefficients and you transform y into lambda, and you transform the order of differentiation into a power of lambda. So that y double prime becomes lambda squared, y prime becomes lambda to the first power, and y becomes constant because y has no derivatives. So in some sense, this is the 0th order derivative, which means here you have a lambda to the 0, which is just 1. So you just replace those, and you keep the same coefficients a, b, and c. Now, according to the types of solution that this quadratic equation has, we will have different types of solutions for the differential equation. We know they will always be in the form of an exponential, but it's slightly more complicated than that. And first of all, once we face a quadratic equation, there are different techniques to solve it depending on how simple it is, but there's a technique that encloses them all, and which is by using the quadratic formula, okay? If I give you any quadratic equation, you can always produce the solutions by using the quadratic formula. So let me remind you what the quadratic formula says. So let's say lambda 1 and lambda 2 are the two solutions of this equation. So they are obtained by computing minus b plus or minus the square root of b squared minus 4ac all divided by 2a. Okay, so that's the quadratic formula. And what's important here is this quantity that is under the square root, which is usually denoted by this capital Greek delta. So b squared minus 4ac. This is called the discriminant. Because it discriminates between different types of solutions of your quadratic equation. And now we're going to describe what happens in each of the three different cases that might present. So case 1, if delta is strictly positive, then in the formula I'm taking the square root of a positive number, which gives me some real number. Then I have plus or minus, so I obtain two distinct real solutions. Distinct real solutions. Lambda 1 and lambda 2. Okay, they are going to be different. One is obtained by choosing plus and the other by choosing minus. Well, now in this case, I know that exponential to the lambda 1x will be a solution of the differential equation, and exponential of lambda 2x will be a solution of the differential equation. Due to the linearity of this equation, I can find the general solution by taking a linear combination, which means I will have constant 1, so c1, times e to the lambda 1x plus c2 times e to the lambda 2x, where c1 and c2 are real constants. Okay, as they vary, this gives me all possible solutions of my differential equation. Now, let's erase that, move this up here. Case 2, this discriminant could be equal to 0. In that case, the square root of 0 is 0, and I have plus or minus 0, which doesn't change my solution, basically. So instead of having two distinct real solutions, I have two solutions that are the same. Okay, you might be used to saying that there is only one solution, but technically there are still two solutions, just they are the same. So I would say two coincident real solutions. Or you can say a solution with multiplicity 2 appears twice. Okay, so it just means that lambda 1 equals lambda 2 in this case. So let's just call this lambda. And so we know that we will have a solution that's e to the lambda x, but since this is a second order equation, it must have two different types of solution in some sense. Here I will obtain c1 e to the lambda x plus, I cannot simply put c2 e to the lambda x as I did before, right? If I were to put lambda 1 lambda 2, because in this case they're the same, because here I'm not really writing a combination of two. This is simply c1 plus c2 times e to the lambda x, and this is just a constant, so basically just one solution. Instead, I will need to multiply this by x, and this will give me the general solution, in this case of two coincident real solutions, as c1 and c2 vary among real numbers. Now the last case is if the discriminant is now negative. Well, in this case, I have the square root of a negative number, which is not a real number, but it is an imaginary number. So in this case, I obtain two complex conjugate solutions. This means they will have the form, let's say, alpha plus I beta and alpha minus I beta, where I is the imaginary unit. So alpha is the real part and beta is the imaginary part. Now in this case, we have complex solutions, but the equation is originally real. So we want to write the solution in terms of real functions. And by using Euler's formula that connects complex exponentials with real exponentials and sines and cosines, we can obtain the general solution as follows. So C1 e to the alpha x cosine of beta x plus C2 e to the alpha x sine of beta x. Again, where C1 and C2 are real numbers. And this completes the picture for what happens in the case of linear equations with constant coefficients that are homogeneous and second order. Okay, this is specifically for second order because it follows from the theory of quadratic equations.